Hi everyone, today I'm gonna give you my second lecture on torsional loading. Before discussing a new contents of today, let me give you a review on the contents we covered in previous lecture. So in previous lecture we covered two things. First, as we have done in axial loading chapters, we discussed and derived how to obtain the deformation out of the torsional loading. Here, the deformation is twist angle phi. Okay, and the equation we derived has a similar mathematical structure with the equation we derived for displacement in axial loading. So here, what we got is external stimuli, which is torsion, torque about the rotation axis, and the length of the beam, and the material property G, which determines the relationship between shear stress and shear strain, because we are concerning the shearing deformation for torsion. And J, this is something similar but different to cross-sectional area. And J is defined for integral over rho squared dA. Rho is the distance from the center, and dA is infinitesimal area of the cross-section, and this integral over the entire cross-section, and that somehow determines the resistance to torque, and so that when we have higher J, because it has higher resistance for twist loading, so you're gonna have smaller twist angle. That's the implication of this formula. And how did we derive this formula? So we begin from drawing a simple middle school geometry relationship. Like if you multiply radius and the angle, which is phi, and if you multiply radius and the angle gamma, then L gamma must be same as C phi, and it must be gamma max, because we are concerning the shear strain on the surface. Starting from here, then we constructed smaller radius inside this pillar. This is imaginary cylindrical surface. Then we can also derive a similar relationship, and based on that consideration, we are able to derive this relationship. The shear strain must be proportional to rho, and it becomes 0 and becomes maximum. It becomes 0 when rho is 0. It becomes maximum when rho is C at the surface, and it has a linear relationship with the rho, which gives us this relationship. Now, after we obtain the shear strain distribution over as a function of rho, we are able to obtain shear stress distribution using material property G, which connects strain and stress. Then, after obtaining the shear stress as a function of rho, which gives us this relationship for shear stress distribution. And if we integrate this shear stress over the entire plane, then we can obtain the torque on the entire plane, which must be balanced with applied torque T. Then after we massage this equation, we plug in the expression for tau, and this is the radius, and tau times dA is infinitesimal force. And if you plug in the relationship we just derived here, this guy, and where tau max is gc phi over L, then what we have ends up is the T must be same as g times phi divided by L multiplied by this integral, and we define this as polar moment of inertia for that specific cross section. Okay, once we define this as J and we write this equation in terms of phi, we obtained the equation TL over GJ, which I just told you in the beginning of today's review lecture. Okay, and after obtaining the twist angle phi, if we plug in this phi here and there, you can obtain maximum shear stress over the volume and maximum shear strain over the volume, and this gives us entire information about like a macroscopic overall torque T, and like a distribution of shear stress and shear strain on the entire sample. Okay, so this is what we have derived for torsion loading and the deformation due to torsion. Then we discussed about stress state. So when we consider x, y coordinate system that is parallel or orthogonal to the rotation axis, then yeah, we see that this is pure shear stress. But however, when we define x prime, y prime axis, like a 45-degree angle from the xy axis, then in this coordinate system we have pure normal stress state. One direction it is compression, the other direction it is tension. Unfortunately, when I was giving lecture offline, I used to have the chalk, and I sometimes and actually always try to break the chalk so that and I want to give you physical sense on how this fracture plane happens, and this fracture plane actually corresponds to the plane with the maximum normal stress. But unfortunately I was not able to do it. So if you have any brittle material in your material which can be broken by your hand power, then please give it a shot, and you might see quite interesting fracture line under the torsion, which is very different from the fracture line in fracture line under the axial loading. Okay, so this is the discussion on stress state for different orientation. Of course, instead of 45-degree angle, if you have different angle, you can have combined shear and normal stress. And regarding combined normal and shear stress, we'll discuss about it in the section and chapter on a Morse circle. Okay, so with that, let me finish the review on previous lecture.